Hello everyone, this is Achintya Mehdi. So in this video, I'll discuss about some basic concept about NMR spectroscopy, which is very important. And if you have not watched the previous video about spectroscopy, links are given in the description below. Please check it and let's start this video. So in this video, I'll discuss about NMR, nuclear magnetic resonance spectroscopy. So this type of spectroscopy is all about nucleus, which is going to interact with an external magnetic field, and there will be a resonance. That means resonance means the nucleus which have some magnetic field, induced magnetic field, which is going to match. Resonance means you can, in simple word, you can say that matching. So that induced magnetic field will match with the external magnetic field, and this is the basic fundamental thing. With the help of, we can explain the technical part of the spectroscopy, NMR spectroscopy. Okay, so as we know that I have drawn here, this is nucleus, which is made up of proton and neutron. So these are electrons. Suppose there are two electrons which are revolving around the nucleus. Nucleus has also spin character. So nucleus always spin around about its axis. Suppose these are two nucleus. Okay, so this nucleus is proton and neutrons are there. So this nucleus is spinning about its axis. This is the axis. Okay, so according to the right hand thumb rule, if the nucleus is spinning in clockwise direction, that means in this direction, nucleus is spinning in this direction, then there will be due to the spinning, there will be a induced magnetic field around the nucleus, and we can conclude, or we can say that the direction of the north pole and south pole of the induced magnetic field of the nucleus will be according to the right hand thumb rule. So if the nucleus is spinning in this direction, then north pole will be in the direction of this thumb. Okay, so as north pole will be here, so opposite to the north, south pole will be the in the opposite direction. Similarly, if there is another nucleus if the nucleus is moving, spinning in this direction, in the anti-clockwise direction, then the direction of the north pole will be in the direction of this thumb. Okay, moving in this direction, spinning in this direction, and north pole will be in this direction and south pole will be here. Okay, so due to the spinning, there will be a magnetic field and also angular momentum. Due to the spinning, there will be an angular momentum, which we can write angular momentum is equal to root over I into I plus 1 into h upon twice pi. Okay, and here I is the spin quantum number. And again, due to the spinning, there will be a magnetic moment, and the magnetic moment we can represent Mi represents the magnetic moment. Okay, and of which direction, magnetic moment's direction will be according to right hand thumb rule. Okay, again you have to know there are two types of particles. And those are fermions and bosons. Okay, so what are fermions and bosons? Fermions are you can say some example of fermions are like electron, proton, neutrons. Okay, so these are fermions, and bosons are like photon and gluons, etc. So photons, gluons are called as boson, and electron, proton, neutrons are called fermions. Now, what is the difference? Difference is the spin of these electrons or protons or neutrons are in fraction. Spin are in fraction. Okay, and in case of bosons, the spin in integer. Okay, now what are those? As we know that angular momentum we write it here like I plus I into I plus 1 h upon twice pi. Okay, here I is the spin quantum number, and the value of I is different for different nucleus. Okay, different particle, the I value of I will be different. So the value of I will be like this. I is equal to n by 2. Okay, where n is equal to 1, 2, 3, 4, 5 like this. Okay, there are different values we have for I. Okay, now if n is 1, then value of I will be half. Okay, if n is equal to 2, then value of I will be 1. Okay, or it will be, if it is 3, then it is 3 by 2. Or if it will be 4, n equal to 4, then it will be 2, like that. Half, 3 by 2, or here it will be 5 by 2, like that. These are fraction, the value of I, where the value of I is in fraction, half, 3 by 2, 5 by 2, like this. These are called fermions. Okay, and this integer 1 or 2 or 3 like this, these are called bosons. Okay, so we can say that if the spin quantum number I is the spin quantum number, so if the spin quantum number is in fraction, half, 3 by 2, 5 by 2, like this, we will say that those are fermions. We can say that those particles which have spin quantum number in 1, 2, 3, 4, 5, like that, we can say that those are bosons. That means photon, gluons have spin quantum number 1, 2, 3, 4, like this. Okay, now this is a nucleus which is made up of proton and neutron, and it is spinning. Okay, so if it is spinning in this clockwise direction, the north pole will be here and south pole will be here. Okay, now if you zoom in this nucleus, it will look like this. This is a nucleus, and suppose there is only one neutron here and only one proton here. Okay, so this is this black colored circle, this is neutrons, and this is black colored, this one is proton. Okay, and this whole part is nucleus. Okay, now this is spinning in this axis, neutrons are also spinning, and this proton is also spinning. So here it will be north pole here, south pole here, north pole here, south pole here. Okay, now we know that neutrons and protons are made up of some subatomic particle which is called quarks. So these are these small circles, these are all six are quarks, are called quarks. These are quarks. Okay, so neutrons are made up of two types of quarks, and protons are also made up of two types of quarks. And the quarks are in case of neutron, quarks are, this is down quarks. This is the name. This is also down quark, and this is called up quark. These are names. Okay, this is down quarks, up quarks. It is not like up down direction, not like that. These are name of the quarks, and this is up quark, and this is up quark, and this is down quark. That means you can see that here there are two down quark and one up quark in case of neutron, and there are two up quark and one down quark in case of proton. Okay, and this down quark or up quark have some charge. Okay, down quarks have charge -1/3. Okay, this down quarks will also have charge -1/3, and up quarks, always up quarks have charge +2/3. Okay, and in case of protons also, as it is up quark, so it will have +2/3, and these up quarks will also have +2/3, and these down quarks will have -1/3. Okay, now if you sum up the charges of quarks in case of neutrons and protons, you can see here for neutrons. Okay, for neutrons there are two down quarks. Okay, so we will sum up -1/3 -1/3 +2/3. There is only one up quark which have charge 2/3. So if you sum up these three, the result will be 0. That's why neutrons are neutral. Neutrons are neutral. Okay, and again in case of for proton, there are two up quarks, so charge are +2/3 +2/3, and only one down quark, so it is -1/3. So if you sum up, it will be 1. That means this is protons. Protons will have charge 1. Charge 1. That's why we write +1 in case of protons, and we say that neutrons are neutral. But these are two different things: being neutral and being discharged. These are two different things. Okay, neutrons are neutral, but it has some subatomic particle which have charge. For better understanding, you can consider a atom. Okay, as we know that one atom, isolated atom, is act as neutral particle. Okay, one atom is always act as neutral particle, but there are some subatomic particle inside the atom which have charge. Okay, so in a atom there are same number of electrons and same number of protons inside the atom. That's why the plus charge of the proton and negative charge of the electron will cancel out each other. That's why one atom acts as neutral particle. And but you can say that there are no charge in a atom. Okay, so similarly in case of neutrons also, in neutrons some subatomic particles are there which are called quarks, where there are two types of quarks there in a neutron, which uh, one type of quarks are positive and one type of quarks are negative. So as the negative part and positive part of the neutron inside the neutron are equal, so this plus part and negative part will cancel out each other. That's why it acts as neutral particle, but it has charge. Okay, so that's why due to the spin of neutron, it will also have some magnetic field around it. Uh, so it will act as a dipole where there is a north pole and there will be a south pole. But similarly, in case of protons, as it has charge plus one charge, so due to the, as we know that moving charge particle will produce magnetic field, so protons will have also a dipole where there will be a north pole and there will be a south pole due to the spinning. Okay, so on the basis of magnetic field of both proton and neutrons, we will say which nucleus is NMR active and which nucleus is NMR inactive. It will depend upon on both neutrons and protons, not only proton. Okay. Now let's discuss the reason behind it. So as we know that if there are two electrons which are in the same suborbital, then we know that the two electrons we write like this. They are in the same suborbital. Now why we write like this? This means that the spin of the electron, the two electrons are antiparallel. That means if there is a electron here which is spinning in clockwise direction, so in case of electrons the right hand thumb rule is opposite to nucleus. So as we know that in case of nucleus, if the nucleus is spinning in anti-clockwise direction, then direction of the north pole will be in this direction of this thumb. Okay, but in case of electron, if the electron is spinning in clockwise direction, then not north pole, it will be south pole. South pole will be in the direction of this thumb. Okay, so if this is spinning in this direction, the south pole will be here and north pole will be here. Again, if there is a electron which are close to each other, then this nucleus should spin in the opposite direction. If this is the spinning in clockwise direction, it should spin in the anti-clockwise direction. Then only the dipole of this electron will be here, it will be south pole and here it will be north pole, and then only this north pole and this south pole will attract each other, and this south pole and this north pole will attract each other. But if both electrons are spinning in the same direction, then here it will be south, here it will be south, north, then this south will repel this south and this north will repel this north, so they can't stay together. Okay, so in case of nucleus also this is similar. So in case of nucleus also, if one nucleus is here, this is one nucleus. Okay, so it should, if it is spinning in clockwise direction, then here it will be north pole and it will be south pole. So if another nucleus wants to stay with this nucleus together, close together, then it should spin in anti-clockwise direction, because this nucleus is spinning in clockwise direction, then it should spin in anti-clockwise direction. Then only the north pole will be in this direction and south pole will be in this direction. Then only it will attract each other. This north will attract this south and this south will attract this north. Then only this nucleus can stay together. Okay. Now you can see here there are even number of protons are there. Okay. So if suppose there are 4 protons are in the nucleus, okay, those 4 nucleus will pair up and there will be 2 pair. Okay, so they will pair up and make 2 pair, and like this there is, suppose this 2 there are 4 nucleus like this, 1 2 3 4. Okay, so these 2 nucleus will pair up and it will be neutral. Okay, as this is moving in the anti-clockwise direction and this is moving in the anti-clockwise direction, so the north pole will attract this south pole and this north pole will attract this south pole. So this 2 nucleus will pair up and become neutral. Again this 2 nucleus will also pair up like this and become neutral. Okay, so that's why, again, if you can see here neutron, there are same 6 number, suppose 6 number of neutrons are there. Here it is 4 number of protons, and here it is 6 number of neutrons. So 6 number of neutrons will again pair up with each other and become 3 pair and become neutral. Okay, so that's why spin quantum number will be 0 and there will be no NMR spectra. It will not show any NMR spectra. Again, in case of this, if there are even number of protons, suppose 4 number of protons are there, and those 4 protons will pair up and become neutral and there will be 2 pair. Okay, so here it is 4 odd number of neutrons are there, suppose 5 number of neutrons are there. Okay, so among those 4 neutrons will pair up and become 2 pair and they will be neutral. Okay, and the remaining neutron, there are 5 neutrons, this 4 will pair up, and only 1 neutrons are there which is not paired, which is unpaired. So this neutron, unpaired neutron, will have spin quantum number half or 3/2 like this. So it will be fraction. That's why due to the fraction of spin quantum number, it will show NMR active, and carbon 13 will show like that. Okay, in case of this type of nucleus, there are odd number of protons are there. Suppose 5 number of protons are there, where 4 protons will pair up and 1 proton will remain. And again, in case of neutrons also, suppose 7 number of neutrons are there, so 6 neutrons will pair up with each other and only 1 neutron will remain there. Okay, so this 1 unpaired proton and 1 unpaired neutron again will pair up with each other. Okay, the remaining 1 unpaired proton and remaining unpaired neutron will pair up, and that's why here 1 unpaired proton will have spin, suppose half, and the unpaired neutron will have spin half, and when they will pair up, the spin quantum number will be 1. Okay, so that kind of those kind of nucleus will also show NMR spectra. So like this. Now when one nucleus is not in the field of some external magnetic field, that means there is no influence of any magnetic field or electric field, and in absence of that magnetic field, external magnetic field, a nucleus can orient in random direction. There is no restriction for that nucleus, so it can orient in any direction. Orientation means, suppose these are some nucleus, so these nucleus are oriented in different direction randomly. So this nucleus, suppose this nucleus is spinning in this direction, this nucleus is spinning in this direction, this nucleus is spinning in this direction. So these are the direction. This is the north pole, this is south pole. So for this all nucleus, each nucleus have a north pole and there is a south pole. So these nucleuses are orienting in different direction randomly, because there is no presence of external magnetic field. So this state of this nucleus is called degenerate state. Now let's discuss the basics of the technical part of NMR spectroscopy. Okay, for that, in NMR spectroscopy, there is a north pole here, a bar magnet, which north pole will be here and south pole will be somewhere in this direction, and there is another magnetic bar which have this south pole in here, and north pole will be somewhere here. Okay, so in between this north pole and south pole, when we will bring one nucleus from the degenerate state where they are orienting in different direction, so we will bring that one nucleus in between this two magnetic bar. Okay, north pole, south pole. So there will be as we know that the direction of magnetic field of any magnet will be in the direction from north to south. So these lines representing the direction of magnetic field of the external magnet. This is external magnet. Okay, and these are magnetic field direction, and there will be some magnetic field strength which is denoted by H naught. Okay, H naught is the magnetic field strength of the external magnet. Okay, now when we will bring one nucleus and put in between this magnetic bar, then automatically, and before that, nucleus is orienting in different direction, in any direction randomly. So after putting in between this magnetic bar, it will automatically orient in this direction where this nucleus is spinning in this direction. Okay, and it will automatically orient itself like this, where north pole will be towards south pole of this external magnetic field, and south pole of the nucleus will orient towards north pole of the external magnetic field, because this north pole will be attracted by this south pole and this south pole will be attracted by this north pole. So in this orientation for the nucleus, in this orientation where this nucleus will orient in this way, where north pole will be towards south pole and south pole will be towards north pole. In that state, the energy of the nucleus will be lowered as compared to the degenerate state. Okay, now in this state, the energy of this nucleus will be low, very low. Now suppose spin quantum number I for this nucleus, let's consider it is half. Okay, so spin multiplicity will be twice I plus 1. Okay, so 2 into half plus 1, 2 will be cancelled out, 1 plus 1, it will be 2. That means spin multiplicity means how many how many orientation are possible for that nucleus is called spin multiplicity. That means if spin multiplicity is 2, that means nucleus can orient itself in 2 different direction. Okay, different way. So magnetic quantum number will be plus half and minus half. Okay, these are 2 possible orientation with which nucleus can orient itself. Okay, so this is one of the orientation here. So as it has low energy, so we will represent this low energy as plus half. Okay, this is one of the orientation. Next, when we will supply energy in terms of light, which is denoted by h nu. Okay, so h nu is the energy of the electromagnetic wave, and for NMR to change this orientation of this nucleus, we needs only radio wave. Okay, so radio wave is sufficient to change the orientation of the nucleus. So when we will supply heat or energy in terms of not heat, we will supply energy in terms of light, this nucleus should absorb that energy, but in this case it doesn't happen like that. So for that we will put here, it is a detector. So when we will give energy or light in the nucleus, suppose we are increasing the energy of the radio wave for 0, 1, 2, 3, 4, 5, 6 like that. So suppose we are giving a light which have frequency 1 Hz. So this nucleus will not absorb that 1 Hz light. Okay, next we are giving 2 Hz, 3 Hz, 5 Hz like that. But for different nucleus, that certain energy is fixed. Okay, so some nucleus will absorb suppose 50 Hz of light, or some nucleus will absorb 40 Hz frequency. But that means for different nucleus it is fixed for that nucleus, that nucleus will absorb only light of that certain frequency. Okay, so we are increasing the frequency of the light, but the whole part of the light will be transmitted through the nucleus and it will fall on this detector, and we will we will get a 100% transmittance. Okay, but when for that nucleus, if this nucleus required 60 hertz light, okay, then when we will increasing and it will attain that 60 hertz light, then this nucleus automatically absorb that whole part, that light having 60 hertz frequency. This nucleus will absorb that. That means at that state, as this nucleus is absorbing that whole part of light, this is called resonance. That means resonance is happening. Okay, so when this nucleus will absorb that light of having 60 hertz, it will flip. The direction of this nucleus will be flipped, and flipped in which direction? It will be in this direction. Okay, so here it will be north pole, here it will be south pole. That means in this state, north pole will be towards north pole of this magnetic bar, and south pole will be towards this south pole of this magnetic bar. So this nucleus, in this orientation, same nucleus but orientation is different. Okay, so in this orientation, this nucleus will have high energy because this 60 hertz is absorbed by this nucleus, so it will have high energy. Okay, again, if you increase the energy, that means more than 60 hertz, suppose 70 hertz, 80 hertz, that nucleus will not absorb that energy because this nucleus need only 60 hertz of light. Okay, so for different nucleus, it is different frequency of light which is needed for that certain nucleus. And this orientation have low energy, which is denoted by +half, and this high energy, this orientation having high energy is represented by -half. Okay, now if you plot a graph for this absorbance, and as you know that it should know that the NMR spectroscopy is a absorption spectroscopy. Okay, this is not an emission spectroscopy, this is absorption spectroscopy. So we will have, after this giving this radio wave, and when it will flip, and we will obtain a absorption spectra. Okay, so suppose this is the intensity direction, this direction representing intensity, and this direction, this axis representing the energy or in terms of frequency. So as we increasing the frequency, we are increasing the frequency, and suppose this much frequency, 1, 2, 3, 4. So as we are increasing the frequency, suppose 1 hertz, 2 hertz, 3 hertz, like that, but the nucleus don't need 1 hertz or 2 hertz or 3 hertz or 4 hertz. It needs 60 hertz. Okay, suppose it you should consider 60 hertz. So in those frequencies which are less than 60 hertz, and those frequencies which are higher than 60 hertz will not be absorbed. So suppose this is 60 hertz, this is 60 hertz. Okay, so in this 60 hertz, there will be no before that 60 hertz, there will be no absorbance. There will be a you will obtain a graph like this, and when that nucleus will obtain that 60 hertz, then immediately there will be a fall here. Okay, in the peak of the intensity, there will be a fall in intensity here. Fall in intensity. Okay, and after that 60 hertz, you are increasing the frequency or energy, but there will be no any absorbance here. This is the absorbance here. There will be a in 60 hertz there will be a absorbance. So graph will be like this. Again, when the nucleus is in degenerate state, that means where there is no external magnetic field. Suppose that nucleus in the degenerate state, there will be a energy. That nucleus will have some kind of energy. So this is the energy level. Suppose this is energy level, and in this direction energy is increasing. Okay, in this direction energy is increasing, and this is a certain energy which is in the degenerate state nucleus. Okay, now when you will bring that nucleus in between these two magnetic bar, automatically it will orient in this direction, and automatically the energy of this nucleus will be lowered, because it feels like stable. Okay, because this nuclear north pole is attracted by south pole, and this south pole will be attracted by this north pole, so it will be a stable state. So in stable state it will have low energy, and this energy will be somewhere here. So we will represent this low energy by plus half. And again, when we are giving some radio wave which have some energy, and that nucleus will absorb that energy, and after absorbing that certain energy, it will flip the direction of the nucleus in this orientation. As spin multiplicity is 2, so there will be only 2 possible orientation. So in this orientation, north pole will be repelled by this north pole will be repelled by this north pole, and this south pole will be repelled by this south pole. So there will be a certain higher energy, or you can say that as this nucleus absorbing that energy, so automatically it will have some higher energy, and which is represented by, and this is somewhere here. Before this energy level, this is represented by minus half. This energy is higher than this degenerate state of the nucleus where there is no external magnetic field. Now let's discuss with different spin quantum number and spin multiplicity how nucleus orient itself in the external magnetic field, and how the energy level will vary. Okay, suppose spin quantum number is 0. Okay, so for spin quantum number 0, I will be what? Twice I. Spin quantum number is 0, so spin multiplicity will be 2 into 0 plus 1, so it will be 1. Okay, so the nucleus will orient in the magnetic field will be how it will orient, because spin multiplicity is 1, that means only one possible way to orient. Okay, so only it will orient in one direction, like this. It will be north, and it will be south. Okay, next in the external magnetic field it will look like this. Okay, and if you draw energy level, it will be like this. Okay, now if the spin quantum number is half, okay, spin multiplicity will be 2 into half plus 1, so 2 will be cancelled out, 1 plus 1 it will be 2. That means two possible orientation for the nucleus in between the external magnetic field. Okay, so how they will orient? One orientation is this one. Okay, so this is, suppose this is low energy, this is having low energy. Another orientation is in this direction, north, south, and it will be high energy. Okay, and energy level will be, this is the degenerate level, where energy level will be for the degenerate nucleus is this one, and for plus half it will be low, and for minus half it will be high. Next, when spin quantum number is 3 by 2, okay, then spin multiplicity will be 2 into 3 by 2, 2 will be cancel out, only 3 will be here, 3 plus 1, 4. Okay, so there will be 4 possible orientation. Suppose okay, so we can represent it this. If spin quantum number is 1, okay, so at that time spin multiplicity will be 2 into 1 plus 1, so 3 possible orientation. And we can represent it like this also. So this orientation, where the direction of the north pole south pole will be perpendicular to the external magnetic field, we can say that at that state we can say that is in as neutral, so we can represent it by a 0. Okay, so this is also same, this is the direction of the north pole south pole will be perpendicular to the external magnetic field, so we can write here 0. Okay, next, if the spin quantum number is 2, okay, then spin multiplicity will be 2 into 2, 4 plus 1, so 5 possible orientation. So these are 5 possible orientation, can represent it like this also. Thank you so much for watching this video. If you like it, please subscribe my channel and share it with friends.